Here is one of the famous pictures of the early discovery from 2012 of the Higgs particle. And you can see the Higgs particle is this bump here. And here, the dots are the experimental measurements, and the red, the dotted, the dashed rather, and the solid red lines are a model. In this type of experiment, you do a very simple model of so-called background plus signal, and the dashed is the background, very smooth, assuming it would have no particular structure at any given mass, and then superimposed on that is the signal, which is interpreted as the Higgs, decaying in this case the two photons. I told you most particles don't go to, I mean, there are a few pi zeros go to two photons, but pi zeros don't have a mass of 125 GeV. They have a mass much less than a GeV. So there is no ambiguity between pi zero and a Higgs. And this plot at the bottom here comes from this model. It is the signal part of the data. This is what happens when you take the data and subtract the background. So you see a nice peak. So before we discuss a little more on that, we will do some codes, this Python codes that generate such peaks and see whether they stick out or not. Let me just make a personal comment. I still remember when I was an undergraduate at Cambridge University, and a distinguished professor at that university got up and gave a talk on what was called high energy physics or particle physics in those days. And he told me that this was a particle, this bump. And I was absolutely amazed because it didn't occur to me a bump was a particle. I thought a bump was a bump. And so that lecture was one of a few at that time which actually convinced me to do my PhD in this area, because I felt the other lectures, which would always, as far as I could see, solving Poisson's equation, del squared phi equals plus or minus 4 pi rho, they struck me as rather obvious. I understood them. They weren't very exciting, whereas this was staggering, bumps being particles. And I'm not certain that's a very good reason to decide one's career, but it did decide my career because I stayed in that field, went to initial university Caltech and as a faculty member, and then at Caltech I went more into computing. But all this started by the professor telling me that this was a particle. We now want to make a little bit of comments on the sort of analytics and I pointed out to you that this is sort of statistics. Notice these points here have error bars, and it's these error bars which go like the square root of the number of particles. And in this total signal, there are around 2,000 events, but actually in each of these bins, there'll be far fewer than 2,000 events. So, and actually these error bars probably have more than the statistical errors and have so-called systematic errors also built into them. So understanding errors is extremely important, and that underlies a lot of the analysis of these so-called counting experiments. So here is some of this detail, which I've already given some of it, 17 miles long, 330 feet below the surface. That's whatever it is, around 100 meters. There's 9,300 magnets, and those are super cooled, very near absolute zero. That's so that they keep their superconductivity. And because of that, the actual electricity cost to run this accelerator is acceptable. If you had to have magnets which had high magnetic field, which were not superconducting, you could not afford it. and these protons get up to very high velocities, let's say 99.99% of the speed of light. And the 6 detectors of those 6 experimental apparatus we already discussed, which 2 of them, ATLAS and CMS, are the general purpose detectors. And it's still, in spite of all the superconductivity, there's a lot of electricity that is needed, 120 megawatts to run this accelerator. It took 10 years to construct. I pointed out that this is a huge activity. And in fact, the fact it's such a huge activity is one of the reasons I left this field. I used to do experiments, and I just found that computing was advancing faster than physics because it did not take 10 to 20 years to plan and build the next experiment. You can go through many generations of Moore's, many turnovers of Moore's law in that time. And the total cost, as it points here, is almost $5 billion. And just running the computers is $286 million annually. And we pointed out just electrical powers are a lot. And the total operating budget for the LHC is about $1 billion per year. So that's the actual accelerator. You also have to pay the experimentalists to run the experiment and to do the analysis, and I mentioned those numbers a little later on. It's about again the same general magnitude, $500 million per year. So this was started in 2008, and it shows that you have to be persevered. The initial runs did not get enough data to really be significant, and only in 2012 was it clear that the Higgs had been discovered. And then somebody found out that it cost $13 billion to discover the Higgs. I don't want to go into whether that was worth it. As it points here, there are many billionaires, maybe some of those associated with other big data things, like some of the social networking sites. I don't know that those are worth 13 billion, but they're quite high. So the Higgs is up there. It's big science, big cost, and it's worth it because it is absolutely fundamental. It tells you about the nature of the forces governing everything, all the particles that make us up.